All right, so I'll get started. First off, I am Jack Minardi. I'm co-founder and software lead at Voxelate. And at Voxelate, our first product is a multi-material 3D printer. I'll talk a little bit about the 3D printer first. We have like I mentioned before, a multi-material platform. We are launching at first with two materials, both a traditional plastic like you would see in the MakerBot or other consumer printers, and we have a second head that extrudes a conductive paste. This is a conductive paste that we developed in the research lab. It's highly conductive, cures at room temperature, and it's about 20,000 times more conductive than other conductive 3D printing materials. We've integrated a pneumatic dispense system that allows you to dispense a large number of materials. So we've designed the heads to be modular, and we will soon be releasing more and more materials to swap in. So some that are coming down the line are epoxies and silicones and things like that. And you'll just be able to pop those materials directly in, and our printing platform will know how to extrude them. We've also integrated a laser profilometer, basically a laser distance sensor, and that allows you to kind of probe the bed, figure out the exact plane of it, and also it allows you to get feedback on your print while you're running the print, so you can come over and scan some of the lines that you've just drawn and make sure that the extrusion volume is correct and the height is correct. This is a time-lapse video of one of our more popular demos. It's a quadcopter that we printed on our device. You can see we've printed the body of the quadcopter, stuck in a control board, and then printed traces out to the motors and up to the LEDs. Okay, so the crux of this talk is Euclid, which is our slicer. So what is Euclid? Euclid is a high-performance path planner for 3D printing written in Julia. Path planning, which is also known as slicing, is the process of taking a 3D mesh, so any number of 3D files, and converting that to something called G-code, which is basically a collection of XYZ moves, like move here at this speed while extruding. And I'll talk a little bit more about both of those in more detail in a bit. So why did we choose Julia? First reason is path planning is computationally expensive. Slice jobs can run on the order of minutes, so speed really does make a difference to us. I came from a Python background. I did scientific computing in Python for a while, and from that background I know that the expressiveness of a language matters. So being high level and allowing you to iterate quickly makes a big deal, especially when you're a small startup and people demand a lot of features. The third reason is PyCall. Doesn't get much credit, but it really provides a bridge to a humongous world of Python packages. While it's not going to be as fast, they're at least there, and you have access to everything that you had access to in Python. And Python has a very large number of libraries that are usable. And the fourth reason is I'm young and naive, and no one can tell me not to use Julia. So this quote from Paul Graham, I think, sums up partly why I decided to use Julia. This is why he's talking about using Lisp in his first startup. A company that gets software written faster and better will, all other things being equal, put its competitors out of business. And slicing is the core software that we do, and we want to do that fast and iterate quickly. So this is a quick architecture overview of our whole entire system. We have Euclid, which is the slicer. Euclid itself is just a command line application. It doesn't know anything about the web. It doesn't have a nice GUI. You access it from the command line, you input files, and it outputs G-code. We've wrapped up Euclid and all of its dependencies in a Docker container. So that makes it easy to deploy wherever we need to. And then we put a Ruby on Rails front end that is able to spin up these Docker containers on command when a slice request comes in. That Ruby on Rails front end is the core API, and we have other clients of the API. So we're working with Autodesk to develop a design software to allow you to design circuits in 3D. That talks to our core API. All of our printers are networked, and they're in communication with the API. And there's also a user front end called the dashboard that users can log into and start and monitor slice jobs. This is a screenshot of our require file as of a few days ago. These are all the packages we're using. Not a very large number, but I thought it would be informative to show what we're using. So I'm going to quickly go over at a very high level what it takes to go from a 3D model to output G-code. The first step, of course, is get a 3D model. Like I mentioned before, we're working with Autodesk to develop some software that allows you to easily design 3D circuitry. But really all we need is a mesh file. And popular mesh file formats are STL and OBJ, and it's basically just a collection of triangles in 3D space. So the next step, once you have the model, is to slice it into polygons. This is basically intersecting your model with planes, increasing planes in Z, and out come the polygons of intersection. After intersecting and slicing your model, you are going to inset. Offset is what the term is in geometry. That is growing or shrinking a polygon. And you want to offset for two reasons, really. You need to do at least one offset because if you can imagine, the filament that you're extruding has some width. So you need to shrink your polygon a little bit so the edge of your filament is equal to the edge of your input model. But usually you do more than one offset, 2 or 5 offsets. This increases print quality and integrity. And you can see a few offsets on the model there. The next step is to infill the model. That's basically taking straight lines and just putting them inside your model. This fills up the model with plastic and makes it more solid and dense. And you can choose the density of the infill anywhere from 0 to 100%. So at this point, you've generated all the lines that you need to execute to build the part. Now you need to choose what order you execute them in. And we optimize the path order by selecting nearest neighbors and stuff like that, which I'll talk about in more detail in a bit. And once you've optimized, you take all of those lines and turn it into G-code, which is an ASCII file. So the first step is design. I'll go over this quickly. Like I mentioned before, we only need mesh files, which can be output by any number of CAD programs like SolidWorks or Maya or OpenSCAD. But we've partnered with Autodesk to develop an easy-to-use software pipeline that allows you to design your circuitry in 3 dimensions. And this is a screenshot of the current beta version. You can see you basically import your plastic model, and then you can click and drag and draw circuitry in 3 dimensions inside of there. And there's also a large library of components that you can place inside the part, and it'll do a Boolean subtraction of those components, giving you a place to insert them. So out of Autodesk and many other packages, they can export mesh files. 2 of the very common mesh file formats are STL and OBJ. These are pretty similar but have one big difference. An STL file is basically just an array of triangles, of 3-dimensional triangles. Each triangle is defined by 3 vertices. And so it's just a big long list of vertices. You can see on the left that is a snippet out of an STL file. An OBJ file is slightly different. It has 2 arrays. One array of vertices and then another array of faces, which are just integer indexes into the vertice array. And that can save space, and it's slightly more efficient because when you have a mesh, multiple faces share the same vertex. Triangles that are right next to each other will share two vertices. So this allows you to save a little bit of space there and be more exact on what you mean. So to import these files, we use a package called Meshes, which is currently living under the Julia geometry umbrella. Meshes provides three main types, the vertex, the face, and the mesh. You can see a vertex is just a type alias of a length 3 vector. A face is just a collection of 3 vertices. And a mesh is stored similarly to an OBJ file where you have a vector of vertices and a vector of faces. So the main mesh type maps very closely to an OBJ file. So the next step, once you've imported your mesh, is to slice it. We also use meshes here to slice. It's quite easy. You get a handle on your mesh object, you can call slice with the slice heights that you want to slice at. And out of there come the polygons for each height that you gave it in the input array. This is a screenshot of a mesh on the left and all the slice polygons on the right. So you can see a number of polygons were extracted at every height that we requested. Okay, the next step is offsetting. This is a definition of offsetting I got from a popular paper on the topic. The inner offset with distance d of a polygon is the boundary of the set of points, each of which contained inside of P and is a distance greater than d from the boundary of P. So if you look on the right, I have a square offset, and it seems very easy. You just scale the square, right? You shrink it down. That seems easy with a square, but really, it's actually not that easy at all. When you have non-square polygons, you get things like self-intersections when you inset the polygon. So I've zoomed in here on the A in the Julia logo, and you can see that on the third inset, the A has intersected itself, and we've actually 2 polygons came out. So you basically have to inset each of your lines, and then calculate line overlaps, and then regenerate all your polygons from that, which is kind of expensive to do. So you can see on this A, there are really 3 polygons that came out of the innermost inset. So this is a tough problem. We tried for a while we tried a few different approaches to do this. Our first approach was homegrown. We decided to just read the papers and implement our own algorithms. It seemed like a good idea at the time. It was hard. It ended up being pretty tough. All of the literature describes the algorithms in terms of linked lists and old school ways to do things, which is just not very Julian. But we tried that for a while, and we got a mostly working solution. 99% of the time it did the expected thing, but it was slow. And 1% of the time it didn't do the expected thing, and that kills the print. So we abandoned this because slow and hard to debug. These algorithms are tough. So the next thing that we attempted to do was use Clipper. Clipper is the gold standard in polygon offsetting and clipping algorithms. It's written in C++. It's used by many other slicing packages. We wrote a wrapper in using CXX. You can see our wrapper on our GitHub. However, we abandoned this as well because we had to use an unstable Julia, unstable CXX, and unstable LLVM. So not ready for production. But when it worked, it was awesome. We want to get there eventually. Our third and final approach was call into Python. So not very elegant, but it works. There is a Python wrapper of Clipper, so you can just import, within Python, you can just import Clipper and use all of its methods. We used PyCall to call into that, and it works. And what was really nice about this approach is we spent like probably months trying to write our own, and then weeks trying to wrap it in CXX, and then we did this in like a day. So using PyCall, while not elegant, it works. And this is what we're currently doing. Although ultimately, when the necessary libraries mature, we would very much like to use CXX and call out directly into Clipper. So the next step, like I mentioned before, is infill. Once you've offset your polygons, you have to infill them with lines. So infill utilizes clipping, which is the intersection of two polygons. Clipping also more generally refers to any of the Boolean operations on polygons, but here it's the intersection. Clipper does this, obviously, it's called Clipper. So here I've done a little graphic of the intersection of these two polygons is that interior. We generate our infill by generating parallel lines across the whole bounding box of the polygon, and then we clip all of them against the subject polygon. And out come the number of lines that we need to execute to recreate our part. So next step is optimization. At this point, we have all of the lines we need to execute to build our part. They're kind of in a somewhat random order. We have them ordered by layer, but they're absolutely not in an optimal order. So this is actually essentially the traveling salesman problem. We have all of these places we need to go. How do we pick a quick way to get to all of them? And our two goals here are minimize the print time and maximize print quality. And one of the ways that we minimize print time is minimize the amount of travel moves. And a travel move is moving the extruder head without extruding anything. So we basically want to do all of our moves while printing something. That minimizes print time. We also want to minimize retractions. So on a long travel move, we actually have to run the extruder in reverse and suck out some of the plastic because the plastic tends to ooze as it's molten. So we basically really want to minimize long travel moves. Shorter travel moves are acceptable, longer ones are not. And that is a print quality issue because when you unretract, you never get the exact amount of plastic again, and you get surface quality finish errors. So to reorder, we can do things like select which point on the polygon we start at. We can do things like select which polygon to go to next. We can select which infill to go to next. And we try to group, let me jump up here actually. Whoops, wrong way. We try to group polygons into, or try to group lines into logical groups. So like the dot on the top of the J, we would want to print the perimeters and the infill before we jump to another part. So things like that are the optimizations that I'm talking about. So once we do that, and right now we are basically doing a nearest neighbor search on all of the polygons within a given object. So within the dot on the J, we do a nearest neighbor search to find the next infill line to go to or the next polygon to go to. This has room for improvement, but it works pretty well for now. Okay, so now at this point we have all of the paths we need to execute, and the order we need to execute them in. So we need to output G-code. G-code is basically an ASCII language that describes a series of XYZ moves and how fast to move to those points, as well as whether or not to extrude while moving. And there are a few more things like pauses and stuff like that, but it's very, very simple. G-code was actually invented here at MIT in the 50s to control CNCs. still used today to control CNC machines, but the 3D printing community has adopted it as well, because 3D printer is very similar to a CNC. There are various flavors and implementations of G-code, but they all share a common core, like the motion commands are all the same. This is a quick snippet of what G-code looks like. Not very friendly for humans to read, and believe it or not, some people write this by hand, which is not fun. G0 is travel, G1 is travel while extruding, essentially. And so that first line, you can see G0, we're moving the E-axis negative 0.3 at a speed of 960 millimeters per minute. And the E-axis is the extruder, so that's a retract command that pulls the plastic out of the head. Then we move to a certain XY location at a certain speed. Then we unretract by moving the extruder positive direction. And then the fourth line, we move to an XY location while also moving the E-axis. So that's extruding plastic while moving at a speed of 3,000 millimeters per minute. Okay, so that is the overview of Euclid. And like I said before, it's just a command line app. You call it from the command line. You invoke it with Euclid. You give it a path to a JSON config file that specifies things like how fast to move during travel, how high to slice each layer, and lots of various things that you may want to configure. So you give it a path to the config, and then you give it two mesh files. One mesh file representing the plastic, one mesh file representing the silver. And out of there comes G-code. So we have our command line application. We want to put it on the web. We decided to use Docker for this. And what is Docker? The Docker people describe themselves, they say, Docker allows you to package an application and all of its dependencies into a standardized unit for software development. So that sounds exactly like what we needed. We used it, and it's worked out pretty well for us. Why did we do it? One of the reasons was we use AWS, and we didn't want to be dependent upon Amazon. So they have a strange EB extensions syntax that you're supposed to use to spin up new instances. That's only useful if you're using AWS. They also want you to run Amazon Linux, which is almost Red Hat, but slightly different. We didn't want to be dependent on any of that. So we Dockerized our application, and then we just installed Docker on Amazon, and then everything else is our own. It's also really easy to test. So we actually run our unit tests on Jenkins using the same Docker container that we run in production. So we're sure that our tests are running the exact same thing that we're using in production, which is pretty nice. This is a snippet from our Docker file, pretty basic. We start from an installation of Julia on Ubuntu. Then we install the packages we need, so Python, SciPy, PyClipper. And then we run some Julia code to install our Julia packages. So we have two that we use, Polygons and Euclid itself. We install both of those, and then we run the build command for Euclid. Okay, so we have our Docker file that's running Euclid. Now we need to expose that to our users. Like I mentioned before, we built a RESTful endpoint using Ruby on Rails. And people can request to start a job. They can request status from a job. They can post and read config files. And this is all after you've authenticated as a user. So the client workflow looks like this. First, the client posts a new job to our jobs endpoint, and they tell us the config they want to use, and they give us the mesh models that they want to slice. The core API returns a job ID that represents the slice job that was just created, and the client can then request information updates with that job ID. So they can ask what's the progress of this job, and once it's done, they can ask for a link to download the G code for that job. Inside of our Rails application, we currently just shell out to Docker exec, spin up a new Docker container for each one of the requests. So you see we're calling Docker exec, and then we're basically just calling the Euclid command line invocation. And then when Euclid finishes, it just writes the G-code to the file system like it knows how to do. And that happens to be a shared file system that the Rails server also has access to. And then the Rails server grabs that G-code and puts it to an S3 bucket. And then can give out a link to anybody requesting that G-code. Okay, so that's our API. I mentioned also that we have a front end for our users to interact. It actually doesn't look like this right now. It looks like Bootstrap. But our designer mocked these up, and this is what it's ultimately going to look like. So this is the main page that you land on. You can see all of the models you've sliced, including a rendering of the model. You can download the G-code. You can see some stats about that model, like how long it took to slice, how long it will take to print, how much materials it'll take to print, and various things like that that you might want to know. And you can also create a new model from here. And there's a endpoint that allows you to drag and drop your models in and specify a config. This is how you design your configs. Right now, they're just JSON files, but ultimately, it's going to have a nice UI that allows you to point and click on the things that you want to do. And also, like I mentioned before, all of our printers are networked. They're always talking to the core API. So once you're logged in, you will be able to see the status of all the printers that you have on your account, whether or not they're online, whether or not they're currently printing. And if there's an available printer, you will be able to send a job directly to it from the web interface. Okay, so conclusions. The speed at which we've been able to develop this has been incredible. If we were doing this in a more traditional language like C or C++, we wouldn't be nearly as far as we got today with the amount of developers, and we wouldn't be able to respond quickly to customer feedback on what features they want. Even though Julia is young, there's a large number of packages that we found useful. Julia itself is very stable. We haven't had any issues with core Julia, and we've stuck with the stable releases, so we're still running 0.3 right now, and no issues with that. Also, most of the packages are very stable. Any package that claims to be stable, we've mostly not had an issue with. I really like how easy it is to install and manage packages, as they're just Git repos. That's really nice. And finally, if there is no available package, like I mentioned before, PyCall. PyCall is always there. One more. Even though Julia wasn't explicitly designed for the web, and I know there are some packages getting started that'll make this easier, Docker just makes that very easy to put Julia into the cloud. And I thought I would also throw a wish list up here. This is what would really help us at Voxel 8, a stable 0.4. In particular, package pre-compilation and doc strings, which I know are very close. Also, CXX and a debugger, and that's all Kino. So, good luck. And I want to conclude with a let's see. A time lapse of the Julia logo that we just printed. So you can see there, printing. And, whoops. And we embedded, how do I? I guess I have to go all the way to the end. And we've embedded LEDs inside of the logo and power them and turn them on, blink. So with that, I'm done, and I'll take questions.
Between which components of your system is 0MQ used, and why is it used as opposed to some other protocol like a RESTful interface?
So we experimented with 0MQ. We're actually not doing that in production right now, but we used it to keep a Julia process running because the startup time with all of our packages is about 15 seconds. So we kept Euclid running, and then we would send it jobs over 0MQ. That's just the way that we experimented with, and it worked pretty well. But ultimately, we decided not to build our system with the assumption that Julia would always take 15 seconds to start up, because we expect that'll change soon. But 0MQ is easy to use, and we were able to talk from Ruby to Julia with no problems. Pretty much every language has bindings for 0MQ. That's why we went with it.
So how does the performance between the CXX wrapping of Clipper and the PyCall wrapping of Clipper?
I don't have exact numbers, but it's actually not that bad. I think the PyCall version is like 2 or 3 times slower. So yeah, I mean, it's not Clipper in Python. It's still C++, just with a very thin Python communication layer. Most of the heavy work is still done in C++.
Where can I get a light up 3D printed Julia logo?
I can give you this one.
So how long does a typical job take in the back end? How many seconds of computation time? Second question is related to the first. Are other 3D printer companies having the same model? I mean, I understand the advantage of doing your computation in the cloud because you could, I guess, update your algorithms easily. But is that a standard thing going forward in the industry, or is it something that is unique to your setup?
Okay, so the first question is how long does it take to slice? This logo took maybe 30 seconds, something like that. The second question is it standard to do slicing in the cloud? And the answer is not really. Most of the popular slicers are run client side. There are a few, but no, not really.
I have one actually.
Sure.
You said 0.4 is one of your wish lists. What in particular are you looking for in 0.4? And given that you already have stuff running in 0.3, how keen are you to move to 0.4?
Okay. So the question was, what do we want out of 0.4? Like I mentioned, doc strings and pre-compilation are 2 big ones that would be really helpful to us. And we've been using compat, so the transition to 0.4 hopefully isn't that bad. Every once in a while we run on 0.4 to make sure things are working, and it seems to be going pretty smoothly. But yeah, mostly doc strings and pre-compilation are 2 big things that we want.
Any other questions? Okay. Thank you. Thanks, Jack.
Thank you.